Okay, perfect. So today we have to continue the movements of future random life random variable topic, and then we can move on to the life insurance topic thereafter. So yeah, I'll distribute the life insurance material after the completion of this topic. So last week we discussed about the movements of future random uh, lifetime random variable using these three equations, and we discussed one example as well. So let's jump into the example 11. In here, we are given the force of mortality, but it is a step function and it's a constant um, in each step. So we can see it's zero point zero 0.04 in between 0 and 40, and zero point zero 0.05 after 40. And we need to find the continuous expectation of a person who is at age 25 and for the next 25 years. So this is a circle to indicate it is continuous and age is 25 and we are considering it for 25 more years. So this is the part we need to evaluate. Um, if you look at this, so we know it goes from 0 to n, but starts from 0, which means the age is x. But if we look at the mortality, the force of mortality, it's given in the range of actual age x. That means uh, we know that when we are given the force of mortality, we can find the survival function. So if we know, so this is the survival probability, which is a function. And if we know the force of mortality, we can find it like this. So if this x is in between 0 and 40, this is a constant, and we integrate it with respect to u, and you will get this for the range from 0 to 40. But in our case, mm, x is 25. That means if you get 0 to 40 and 40 beyond, so we are almost past 25 years. Now we are in here. And surviving for 25 more years means we have 15 years from 25 to 40, and then it goes for 10 more years. And because of that, our T, or the future lifetime, starts from this point and goes towards the positive infinity, so that our T is 0 at age 25. And at age 40, T is 15 and beyond. So what we can do is, like, we know the form of the survival function is kind of an exponential function with mu times t. That means from 0 to 15 and from 15 onwards, we can use two different mu's and write down the probability of a person who is at age 25 surviving for t years as probability of a person who is at age 25 surviving for 15 years, and a person who has survived 40 years. So now the age is 40. Please wait. Okay, yeah. Age is 40, and the remaining lifetime means t minus 50, because from the future lifetime, this person has already survived 15 years. So if we decompose it like this, then using this equation, we can find the person who is at age 25 surviving for 15 years like this. And then the formula for this survival probability is the person's age. So this person has already survived 40 years, which means it belongs to the second step of the force of mortality. And it goes from 40 to t minus 15. That means I can write down the probability goes from 0 to t minus 15 since they have survived for 15 years after 25, but the future lifetime is t, so that means we need to take that 15 years out of the future lifetime for this person, and the force of mortality is 0.5. We can integrate with respect to du, and this gives, so this is the compound probability of survival for this person. And if I simplify this, I'll get an exponential function like this. And now we know the survival probability for this person. And from the definition, to find this limited term expectation, I can define it like this. Since we have two different survival functions for both regions, says this plus from 15 to 25. That means for the first jump, we have this, let's say, the first survival function. And for the second one, or the second stage, we have the second survival function, which is this. And yeah, for this one, we know it is this. And after that, we can simplify the integrals, where if you integrate this one in between 0 and 15, it's 40 over 0.4 from 0 to 15. And for this one, there's a constant, and then the function is this. So the limits are 15 to 25. And if you simplify this more, you will get the answer like this. So in this question, you could see we have two regions in the age type or the age line because it's given in X. So from newborn age infant to a person who is at age 40, they have zero point zero 0.04 cause of mortality, and who are older than 40 years, they have 0.05 cause of mortality. Since we have to start it from age 25, that means when we are considering 25 more years, so we have to take 15 years from 0.04 region and the remaining years from 0.05 region. That means for these two regions, we have two different survival functions. First one is straightforward, just the definition. But for the second one, we have to decompose it, like surviving from 25 to 15. And if they survive for 15 years from 25, they are now 40 years age, and the remaining time is T. But since they have spended spend 15 more years, so we have to remove that 15 years from the future lifetime T. So then we can apply for this probability using the definition, and we get this function. Then we have to apply the definition for the limited expectation of a person who is at age 55 for the next 25 years. Again, we have to think about the division from 0 to 15 and 15 to 25. Then use the respective exponential functions for the survival probability and integrate it. You will get the final answer. So now you can see, though we have the um, assumption of constant force of mortality, still we need to do some integration if by considering the ranges of the force of mortality function if it is an step function, but if it is a direct function, which is just a constant for the entire lifespan, so then our uh, computations will become simpler. So that is the story of this future lifetime or the calculating the movements of future lifetimes, and those are for the continuous random variable. Now we can quickly go into the definitions of the current future lifetime random variable and the respective first movement and the second movement of those uh, current random variables. So in this page, I will quickly derive what we have listed there. So as it is given in the definition, so EX without the circle, it says the expectation of the current random variable, future lifetime random variable of a person who is at age X. And the expectation means we need to get the summation of all terms, which is the multiplication of K and the probability of observing Kx equal to K. And this is same as A times this. And we know that means k start from 0. The first term is 0. And surviving from age x to 0 years. But this is the first year, which means starting from x, we only go for the next year, x plus 1. So then if k is 1, that means the person has already survived 1 year and surviving for next year. And if it is 2, person has already survived 2 years and surviving for the next year. So likewise, I can expand this x 3 and surviving for the next 1 year. So this goes to infinity and it creates a series and which is like this. So this term become 0, but for this term, I can say surviving from x to 1 and then the death occurs from the next year with this. And for this one, 2 times surviving from x to 2, death occurs within the next year. So likewise, I can use the definition and expand this multiplication. Oh, now it's a series. So you can see I can rearrange uh, no, I think yeah. So before that, let's do we have 1 here, 2 here, this one. And for this one, it's x to 2. This is yeah. I think without going expanding this, let's expand it like this. So this is also a possible way, but if you want to make it a series, let's try this. So this is 0. That's okay. So for this one, it's surviving from x to x plus 1 and death occurs between x plus 1 and x plus 2. So survives and death. That means this deferred probability is the difference between the survival probabilities. So this is surviving from x to x plus 1. And if I get, so let's say like this. For this jump, it's surviving from x to x plus 1. For this jump, it's surviving from x to x plus 2. And if you get the difference in between these two survival probabilities, it's the deferred death probability of a person who is at age x, surviving for x plus 1, and death occurs within the next year. So we can use that concept in here and directly come from here to here like this. So for this one, it's x minus 1 and probability from x to 2 times probability that x to 2 minus probability x to 3, and for this one 3 times probability from surviving from x to 3 and x to 4. So now we can see pattern in this, and then since we rearrange this, we can think of getting this, and since we have 2 px to 2, which is positives, but we have one negative value here. So if we simplify these two, we get 2 times px2. Like in here, we have 3 positive px3s and 1 negative px3. That means, so in here, actually it's 2 because you have to multiply it by 2. And for here, we don't have, so in here it's 1. And again, we have 1 px3. If I expand it, you will have something like this. That means this is the summation of k equal 1 to infinity, and the probability start from x and going for ks. So that is how we can derive a closed form for this. So we don't need this expansion, but it's good to have the third, omit the third line and go to the fourth line to have this closed form, which is familiar to us. And in the same way, we can get the second movement for the person who is at age x. And let's quickly write down the definition. Says, so this is the definition, and same as O. So for that one as well, if I expand it, now it's square, and this square q11, 2 square q21, and 3 square q31. Like that, we can use the deferred probabilities and write down the definition as a series of these geometric and arithmetic combination. And now we can rearrange it in the same way. This is 0 for this one. Again, it's the probability difference in between these two times 4, probability difference in between this and like this. So we now get the pattern. And if we simplify this, we have 4 positive terms, 1 negative term, and we have 3 positive terms as a result. And here we have 9 positive terms for px3 and 4 negative terms for px3. It's 5 px3. And if I expand this, so if we had the next term, this should be 16 times. So For px4, 16 px4 positives and 9 px4 negatives. So the difference would be 7. So if I write down 7 from px4, now it's a series and we can simplify it like this. So this is the closed form for the second movement. And if we know the second movement and the first movement, we can find the variance of kx using this familiar definition. And this one is, so now we can find that one. So that's the simple definition of this future lifetime random variable movement. And like in the same way, we can think of the term like for temporary current expectation. Now start from age x and goes to 10 n years, and we don't have a circle. That means it's a current random variable. And for the entire life, it goes from k to infinity. But for the temporary life, it goes from k equal 1 to n. So that's the easiest way to derive it. But you can think it's like this. So when you expand it, so in here, x to infinity. So that's why it goes from 1 to infinity. In here, it goes from x to x plus n. That's why it goes from 1 to n. So that's a way we can uh, recognize or memorize this equation. And the 14th one is a result of the rearrangement of the infinite series, because if I go back to here, you can see, so we had this rearrangement to get the infinite sum like this. But if we take this out, so I'll write it down in here. So Ex is the summation from k 1 to infinity and this. And if I take px1 out from this, it's k to infinity. But now, since I take 1 year out of that one, so they have already survived x plus 1 year. And this become k minus 1. So if k star is k minus 1, this will give E, the summation of k star from, uh, so we need this to be 1, and if this is k star, so k star is 1, if k is equal to 0, okay, that's fine. We'll have this. And it is the future lifetime expectation of a person who is at age x plus 1. And now you will see that. So we need one in here because, so if k is equal to 1, k star is equal to 0. So that means survive from x plus 1 to x plus 1. So it is almost 1. That means times 1 plus x plus 1. So that's how we can rearrange that infinite sum to get this 14th equation. And under the UDD assumption, that means uniform distribution of death. So we can get the continuous future lifetime, expected lifetime, as the sum of the current expectation plus zero 0.5 or half. So that is the summary of equations we can use for current future lifetime random variable movements, the first movement, the second movement, and the temporal life expectation. And this is a recursive formula. So now if we know the value at age x and the probability of survival from x to 1 more year, we can find the expectation at age x plus 1. And if we know the current lifetime under the UDD, by adding zero 0.5 into it, we will get the continuous expectation. So those are the equation we need to deal with. And let's quickly discuss this example where we can find different kind of quantities related to this life table. And we know that from age 95 to 98, the number of survivors at each age gap, oh, this is the 1 year interval. So that means at each age, uh, the number of survivors decreases and goes to 0 at age 98. So the ultimate lifetime is 98. And we need to find the current future lifetime first movement for a person who is at age 95. That means the person is at 95 and k goes from 1 to infinity, but the infinity occurs at 98. So that means from 95 to 96, we have one jump. For 97, one more. And for 98, we have one more. So eventually we have three values, k is equal to 1, 2, and 3. And the probabilities are from 95 to k. That means from 95 to 96 plus 96 to 97 plus 97 to 98. And you know that it's 3 over 4, 1 over, oh, sorry, so this is starting from 95. So at each age, this should be 95. 1 over 4 and 0 over 4. Eventually, it's 1. So this is in years. So that means if a person who is at age 95, the average lifetime we can expect for this person is 1 more year. Or any person in this cohort is 1 year. But from the details, we know that there are 400 survivors at the age 95, but going from 95 to 96, we experience 100 deaths for this group. And from going from 96 to 97, we experience 200 deaths. And from 97 to 98, we experience 100 more deaths, eventually the number of survivors at age 98 is 0. That means, on average, a person who is in this group can survive for one more year. And now we need to find the variance of the current future lifetime random variable at age 95. That means we need to find the second movement of this current random variable. And it is given by, since we know that now k is going from 1 to 3, so we can directly use this definition. And when this is 1, this is 1 times the probability from 95 to 96. That means L96 divided by L95. And when it's 2, it's 4 minus 3. That means 3 times probability from 95 to 97. So 97 over 95. And when it's 3, it's 8. It goes from 5 to 98. So we know that it's 400. And for this one, it's 300. And for this one, it's 3 times 100, 8 times 0, which is 1.5. And now we can find the variance of this current random variable as 1.5 minus 1 square, which is 0.5. And then we can move to part C. So this is part A, this is part B. Let's go to part C, which is temporary life, who is at age 95 and only going for one more year. So we know that from definition, k is starting from 1. Since n is 1, goes from 1 to 1. And the probability is from 95 to k, which is p 95 1 and L96 over 95. This gives directly 3 over 4. And for D, the continuous under uniform distribution of death, we can use the last equation. And this is 1, therefore it is 1.5. And finally, need to get the 96 future lifetime expectation. And to find this, I can use 95 is P 95 to 96 plus E 96. So from this, I can find E96 first, which is, so we know E95 is 1, and this one, it's 300 over 400, which means now it should be 4 over 3 and minus 1, and this will give us 1 over 3. And under the UDD assumption, we can say this, or for this you can like this, and eventually it's this, which is 6, 2, and 3. So now you can see how easily we can manage those calculations if we know these equations by heart, and we don't need to rely on, which means worry about the definitions and how to derive those things, but you can directly use these equations in calculating these values. Like in the continuous case, let's see whether uh, if we are given the functions of the survival probability rather than having the numbers for the number of survivals as a life tape. So in this case, we are given the survival probability function for a newborn infant, and we have a maximum age, which is omega, and for a person who is at age 106, they have a constant force of mortality, which is 1 over 180. Now we need to find the current future expected lifetime for a person who is at life or the life at age 106. Let's say we need to start from somewhere. So to get this expectation, we know that we need the px. So we need to find a form for this one, p 106k. So x is 106 now. If we know this one, we can find uh, the summation of a series of these values where k goes from 1 to infinity. So to do that, we know that infinity is now limited by omega. So we need to find a value for omega first. So let's start it from here. So we know that for the force of mortality, if we differentiate the mu, uh, to get the mu, we need to differentiate the log value of survival function. Because in the previous example, or actually in the 11th, example 11, we integrated mu and then it is in the exponential function to get the survival probability. Now here we do it on the other way, and once you differentiate it with respect to s, we get 1 over 4 times 1 over omega minus x. And now, so age is uh, okay, so in here it's 106 and we need to find the value of 106. I think, yeah, let's say it like this. So we know the value of 106, which is this, and it's also equal to this, because x is uh, this. Let's calculate it using the calculator, where we can find, yeah, I think we need to change this. Let me check the textbook first. Yeah, so this is not 106, it is 65. So that we can have something meaningful for mu and omega. If it was 65, then it is 65. this gives omega equal to 114. Yeah, so that is meaningful. So if I get 106, so omega will go to 151. So that's why I rechecked it. So if we edit this mu 65 as 1 over 180, we will get something reachable for a summation by hand. And now, since the maximum age is 110 and the current lifetime for a person who is at 106, we just need to find four or the probabilities of four jumps. And let's say it's like this. So for this one, I can write it down. Surviving from 0 to x plus. Uh, so in here it's 106, 6 plus k, and divided by surviving from 0 to 106. So that is the 4. And the definition for the curtain expectation is summation of 106 to 1 plus summation of 106 to 2 more years plus 106 to 3 more years. So if we have these jumps 107, 108, 109, and 110. So that means this is the maximum survival probabilities we can get for this life. And for this series, this is a common denominator. So let's have it like this. And for the numerators, it goes from 1 year, that means 107 plus 2 years, 108 plus 3 years, 109 plus 4 years, 110. And now we know the values for omega and know the value for t as well. So you can simplify these. So I'll write down the form, can simplify it later. So the form of this one is 1 minus 106 over this and 4. And for this one, 1 minus 106 plus k or 110 and this. So once you apply 1, 2, 3, and 4 for this k, so we'll get this S naught 107 to S naught 110, and you can find the value of S naught 106 and get the final value using this form. So you will get something near to 2.478. So you can write by yourself. So that's a different sample. So in both curtailed and continuous cases, we saw if you are given the first of mortality and then directly we can find the survival probability, and then using the integration and using one of these three equations, we can find the first moment, the second moment, and the expectation of the temporal life. And this force of mortality can be a step function as well. If it is a step function, then you need to check the life range and match and identify the remaining lifetime of that person. So in this case, since this person was 25, so he had 15 years within the first step and the rest of the life in the second step. So that we need two different survival probability functions and then integrate it with respect to the ranges like this. And then it comes to uh, the current movements. So also a summation of the survival probabilities from x to k more years. But in here, for the second movement, it's 2 times k minus 1 is the factor. And the term life or the temporal life is easy. It goes from x to n, where x to n. And we have a recursive formula as well. And under the UDD, it's just adding 0.5 for the current expectation to get the uh, continuous expectation. So if we are given these values of a life table as a number of survivors, it's quite easy to find these probabilities of survivals for a given age or given time range in future. But if you are given the survival function, that means definitely we need to find the maximum age if it is not given. To find the maximum age, they should give us a clue. So in this case, they have given both the survival function and the force of mortality at one age. What we did was we first used the definition and transform the given survival function into the force of mortality, and it is also a function of x now, and we know a value of this mu x when x equal to 65. So we substitute it and found the maximum the maximum life observed in this sample, which is 110, and then we can apply the definition in here. Since we don't know else, we can directly apply these survival functions, and then we got this value. So now you can see we are just playing with these 3 and 4 equations for continuous and current random variables in different ways, but we always need the equations we got in the second chapter to deal with these equations, because we need to transform these equations into different ways according to the available. So otherwise we cannot utilize the given information. So depending on the given information, we will transform it in different ways and use these equations. So that's the way we deal with these equations to get the future expectations and the second movement of the future lifetime random variable. Let's summarize what we have mm, discussed during these chapters, where we had mainly we had two different examples, where the constant force of mortality and uniform distribution of death. And when the constant force of mortality happens, mu x become just mu, which is a constant. And under the uniform distribution of x, or specifically said de Moivre's law, it says the future number of future lives, or the number of survivors at age x. So it follows a uniform distribution and the maximum with omega. So the number of survivors means the gap between the maximum and x. So the density is 1 over this maximum number. And these are the corresponding functions for force of mortality under these two laws. And this is the survival probability from x to t. These are also functions. And this is the death probability, which is qxt. And this is the density. And this is the expectation of this future lifetime random variable. When it is constant, it's 1 over u. When it's uniform, it's omega minus x over 2. And when it's come to variance, is 1 over ux, and this shows that if mu x is mu, then the future lifetime random variable follows an exponential distribution with mean mu. So it's easy to work with this constant force of mortality when we say as an assumption. Then we know that Tx follows. So this is Tx follows an exponential distribution with that same mu. So under the de Moivre's law, since this Lx is uniform and the density is 1 over omega minus x, so these quantities are corresponding to the uniform distribution for this one. So Tx follows a uniform distribution with 0 and omega minus x. So now you can see that the expectation is this plus this divided by 2, and the variance is this minus this square and divided by 12. So it's easy to work under these two assumptions because the Tx follows exponential with mu when it is constant force of mortality, and if it is uniform distribution of death, that means Tx is uniform like this. So let's quickly go through this example again, and then we can start our next topic or the chapter, the life insurance. So in here also we are given a survival function, but it's not kind of complicated, but it has some similar formation like the previous example. Find an expression for the Sx t first. And this is surviving from age x to x plus t. And we know this value. And the survival function at age as death is given by here. And they says that omega is greater than x and t is less than omega minus x. So that is the remaining lifetime for a person who is at age x. So this survival function has kind of a familiar form now. So if you refer this table, so it's like this. So if x, so in this case, x is 0. So if I apply x is 0 to this, so then it's identical to here. So that means Tx follows uh, a uniform distribution. So this fact shows that T naught follows a uniform distribution between 0 and omega because x is 0. And eventually, x follows a uniform distribution with omega minus x. So by comparing that, we can directly say survival probability is this. Or you can use the definition by itself, which is x plus t over sx, and find this. This is also a possible way. So then we can move to the part B, which is show that mu x, or the constant force of mortality, or force of mortality is the density of this uh, uniform random variable, and we know that if you have this, so mu x plus t is given in different ways. We can take the log value of this one and differentiate it with respect to t, or we can differentiate this with respect to t and divide it by this. So since we did the log differentiation in here, we use the log differentiation. So I'll use a different approach in here. Let's differentiate this one with respect to x and divide it with this. So it gives for this one, it's 1 over omega, and c over omega. Now it's, since it x, this should be x, and eventually it will become omega minus x. And for part C, assuming the future expected lifetime for a infant, newborn infant, is 25, we need to show that this maximum lifetime of this population is 50. That means from this table, we can see if this is a uniform distribution of death, the future lifetime expectation is this. This gives, if this occurs, then this is equal to omega over 2, which is equal to 25, and omega is 50. So likewise, you can use these equations directly and do the calculations. No need to derive those things. The only thing you need to do is just be familiar with these equations. And so in the exam, you are allowed to bring uh, a one page of formula sheet with you as a supportive material. So in that uh, material, or the supportive material, you can write down these equations, but it it is only one page of an A4 sheet. That means we have two more chapters, so you need to organize it in a proper way, because you are allowed only to bring one paper. So that's why I'm said, so in the paper you can mention these equations, so write down these equations and use the equations directly, stating the uh, equation in the correct form, and then do the substitution according to the uh, question. If the question uh, don't it doesn't specify or specifically ask for a proof. So if you are not uh, asked to provide a proof, then you don't have to provide a proof. You just have to use the correct equation and substitute the values to get the uh, final answer. So that is the end of chapter 3, and we can move on to the life insurance part. Before that, I will distribute the material. So, okay, so I have distributed the lecture slide or the material with you. So I will discuss these topics with you now. And then at the end of the day, I will distribute both the completed lecture note for live tables and whatever the content we cover during the next uh, 2 hours in the class under the life insurance so that you can compare later. So up to this point, we have discussed about the methods that we can use to calculate the survival probabilities and the death probabilities of a particular group or a person who is at a specific age, X or 0, and we know how to calculate the expectation of the future lifetime, whether considering whether it is a continuous or discrete case, and also the variance of those future lifetime random variables. And for the probabilities, again, we have the death probability, the survival probability, and the deferred death probability, which is also given in the difference of two death probabilities or two survival probabilities. And also, we can calculate these things or these probabilities using integration of the function or summation of a survival function, or using directly the life table functions, which involves the number of survivors at each age X and the number of deaths at each age. And eventually, we saw that we can use the constant force of mortality assumption and the uniform distribution of death assumptions in different ways to calculate these death probabilities and survival probabilities using the integration and differentiation based on these two assumptions. And finally, we saw that when the uniform distribution of death occurs, the future lifetime random variable follows a uniform distribution. But when the constant force of mortality occurs, the future lifetime random variable becomes an exponential distribution with that constant force of mortality. So now, using all these things, we can we can adapt those concepts into the practical situations in life insurance. So in this chapter, we will discuss a few important life insurance policies. Um, and we will see how we can adapt those probability calculations and finding expectations for the future lifetime random variables um, in terms of insurance and the occurrence of the benefit payment. So still, we have the future lifetime random variable, but now we have new term called the benefit. So we will use simple B to indicate the amount of benefit, and if you so the benefit is the amount being paid to the insured by the or representative of the insured by the insurance when uh, the death occurs or when kind of a claim is triggered. And T, we know that it's the future lifetime random variable. So if you multiply the benefit by the future lifetime random variable, it gives the benefit random variable. So that means, for an example, if you get 100,000 in this year as a medical claim, and if you get 100,000 in 2 years from now, you cannot do the same. You cannot get the same service for that 100,000 uh, after 2 years from now. So because of the inflation and some other cases, the cost of services will increase. So in the same case, we can do more things using 100,000 if we get this 2 years ago, and we can compare the services we could have get or we could have experienced in 2 years ago and the services we are experiencing at this moment for the same amount. That means it's random, and also unless it is an what do you say the life insurance, we can have like, so in here we have this life insurance, but in the medical insurance you will have different kind of claims for the same person. But in the life insurance, the benefit occurs only at once when the death occurs. So that means we know for sure when the person, so we there's only one event and it is proportional. So the risk is proportional to the future lifetime of that person who is being insured by the company. And also we can calculate these uh, benefit payments in two ways, continuously at the moment of the death, or at the end of the year, or at the end of the month of the death. So depending on those two cases, we can uh, divide these insurance portfolios into two main groups: continuous life insurance and discrete life insurance. So in the continuous life insurance, the benefit is being paid at the moment of death. But for the discrete uh, life insurance, the benefit will be paid at the end of the period, which can be month, which can be a quarter, which can be a half year, or which can be an annual payment. So we know that depending on the timeline, how to find the survival probabilities and death probabilities for these fractional ages and also for annual cases. So let's uh, get into the uh, different observations that we can have. And also in the first chapter, in the very first lecture, so we discuss about the interest theory functions. So there I mentioned we will use these present value random variable in life insurance and also annuities. So now we need to use that part, because if I can mm, get the same example I mentioned. So I mentioned that if we are expecting for a medical insurance, if we are expecting to 100,000 of claims in 2 years, that means uh, the company will charge you one or a series of premiums which can cover the cost that we are expecting from 2 years from now. So to get 100,000 after 2 years, so you don't have to pay the exact 100,000 amounts during the 2 years. So you should pay a less amount than the expected amount, but it should not create a financial burden to you and to the insurer or the company. So then what we do is, so the insurer can like insurer can reinvest your premium on a uh, dividend paying bond, or they can lend the money at an insurance rate or fixed rate. That means, so if they take 50,000 from you during this period, and if they can grow that 50,000 into more than 100,000, let's say 150,000, even though you get a benefit after 2 years, the company has sufficient amount of money to pay you 100,000 and also an extra 50,000, which is generated from your money to cover the operational expenses and other wages and expenses. That's how the business grows. So that means the insured person pays the premium, and that premium can be used for reinvest and generate money to cover the benefit payment which is due on future, and also to cover the expenses and profit to the company. That means we can find uh, an interest rate which is a risk-free interest rate, and we can define if I have 100,000 and if I can find 150,000 at the end of this year, that means I know that my the amount in my hand can be grown by 50% of what I have by now. So at the end of the day, the accumulated value will be 150% of what I have by now. So if I convert that conversion, which means the growth, into the risk-free rate, that means I can say something like this. So at zero, I have 100,000, and this I is the risk-free rate. If I grow my fund by 8% of risk-free rate at the end of TX years where the event occurs. So let's say for this TX, let's say T. So now the TX goes from 0 to T, and this is the amount in my hand by the time I face this benefit payment. So now I can use this concept and get the discount value, which is the present value. So on the by applying this, if I need 100,000 at this point, which is Tx equal T, so I should have at least this much amount of money at the beginning. So this is called the present value of this 100,000. And this factor is denoted by V. So when it's come to a random variable, Tx is the random variable. That means in general, I can say the present value random variable is this. Now you will see benefit is also a function of Tx, and this present value is also a function of Tx. So benefit is also a function because one can say that a benefit is 100,000 for the first year, benefit is 150,000 for the second year. So that means when the year changes from 1 to 2, the benefit grows from 50,000. So it's become a function. But most of the time, benefit will be a constant throughout the coverage period. But there are some cases where the benefit increases or decreases with the time. So that means it's safe to denote this benefit function as a function. And now, so the benefit times the discount factor is the present value of the insurance. So you can see 100,000 times VTX is the present value if I'm expecting 100,000 at the by the moment of death for this customer. That means the benefit is 100,000, which is BTX, and 1 over I plus 1 to the power TX is the present value random variable. That means the present value of the insurance is the multiplication of these two. So that's the concept, and we use the same concept for different kind of different types of um, insurance schemes in this chapter. So most of the time, for the ease of calculation, we consider this BTX as 1, and then the Z become the known uh, present value random variable, which is coming from that uh, interest theory. which is 1 over 1 plus I. And when this BTX or the benefit function become a constant, so we call that as the level benefit. So you can say in this occasion, it's a level benefit of $1. So if your benefit is 100,000, you just need to multiply 100,000 by this Z. It is the present value of an 100,000 benefit for this continuous life insurance. So that's easy. Then let's use the same diagram. And if I say, so since our benefit is $1 now, and death occurs at this, that means benefit is paid at this moment. Suppose it is T, and to have $1 at this moment, we should have $1 times VT at the beginning. So that is the picture we discuss in here. So now, so we know this will be the expected value at some point. So I need to decide an amount depending on this future expected value, the expected future value of this benefit payment, uh, which is discounted back to the present starting point, and I should collect the amount from the person who buy this insurance equal to this present value, so that I know that I'm safe. If I'm going with just the risk-free rate, I'm able to cover the benefit payment. I will not have to cover the expenses, operational expenses, so wages or profit for the company, but at least I can meet the benefit payment if the death occurs in future within the covered period. So if now there's a problem in our mind, so if I purchase a whole life insurance, so then I have to take care of this customer for the entire lifetime of that customer. That means there will be a definite benefit payment in future. So in these cases, you should like argue in your mind. So if the present value is the is taken only considering the benefit payment, so then for sure we need to add some expenses amount to this benefit expected or the present value of the benefit payment in order to make some profit or at least break even from this insurance operation. So we will discuss about annuity payments, which is how to collect premium throughout a series of payment in next chapter. So in that chapter, we will discuss how to balance these two and decide the premium amount for a benefit which is due in future in an uncertain point of time, which is not known. But the first uh, insurance type, which is the whole life insurance, definitely there will be a benefit payment at some point in future. That means we need to pay some amount or the death benefit to the insured uh, at the insurer, but we have to make sure that we need to add the expenses of operations and the profit margin to this present value of the benefit payment before we decide the premium. Otherwise, we cannot make any profit or even a break even through this whole life insurance business. So keep that thing in mind. The first thing is we need to calculate the present value, expected present value of the future benefit payment. Since it is continuous, we can say, so we use capital A for the uh, notation. So it says the present value of the expected value of the present value random variable for a person who is at age X, and the death benefit is paid at the moment of death. That's why we use this bar above this A. And it is a whole life insurance. That means, like the expectation we saw in the previous chapter, where we specifically said that if this happens, this is the future expectation of the future lifetime random variable for a person who is at age X. But the end, so it covers from age X to the maximum amount of the lifetime. But if it was like this, then we considered only the life or the age of this life from X to X plus N. That means if the death occurs within this X and X plus 1 ages, the company has to pay. But beyond that, the company has no liability to pay. And we can have different kind of combinations in these cases. So that means we need to develop a proper notation for these present value cases as well. So keep these things in mind. So we will start with this, and in this notation, the bar says it is conti continuous, and this is the expected present value of benefit. This is age. Since we don't have any other kind of uh, symbols after X, it indicates it is for the whole life. So this is continuous whole life insurance. And by definition, it's the expectation of the present value random variable of the benefit payment. And since we assume as the benefit is $1, so now it's the expectation of the present value random variable for the risk-free rate. And since it is continuous, we get the integration from 0 to infinity. But if we had known the limiting age, so it should be omega minus x. And the random variable is b to the power t, but t is the random component in here. So the density function of t has to be included in here. So this is the expectation of a function of a random variable. The function is b to the power t. So it is a function with respect to t. And we know how to calculate the density function if we know the survival probability and the force of mortality. Actually, it's it's sufficient to know uh, the force of mortality, because if we know the force of mortality, we know how to find this survival probability, which is integrating the force of mortality from 0 to t and get the exponent or the negative exponent of that integral value. So we get the density function from there and multiply it from here and integrate it. If you get it kind of a function of t for the integration, so we can use this. So we came v to the power t from e to the power minus delta t as this. Because we have log value of 1 minus 1 plus I is delta. And we know that V is 1 over 1 plus I. So if you get the log value of these two, so it should say uh, V to the power t is e to the power negative delta t. So that's how we got the transformation. So then it's a function of t, and every component, exponent part, the survival probability, and the force of mortality depends on uh, the future lifetime t. And then the other one is, so this is the expectation of present value. So we use capital A. We use A because we say this one as the actuarial present value. So that's why we use capital A. So now I think you are clear about this notation and using the definition to find this value for the whole life continuous case. Then we can follow the same way to obtain the second movement of this present value random variable, where if it is second movement, that means v to the power 2t, and you can do the integration for that part. So once you get it, you can find the variance. So what we can do in here, you can see expectation of C gives e to the power delta t times pxt times mu x plus t. And if you need to find the expectation of C square, then you just need to replace this delta by 2. And in that case, so this is b to the power 2t from delta and fxt dt. This is same as minus 2 delta t fxt dt. So that's why we just need to double the force of mortality in here. So actually delta is the force of interest. So because it's the log value of 1 plus I, so we double the force of interest in here. And this is same as the actuarial present value of a continuous benefit payment whole life insurance for a person who is at age X. This is the second movement. That is how we denote it. And the variance is the second movement minus the first movement square, which is this. So this is inside the bracket. So if you get confusing about that. So that is how that equation is being derived. And in the formula sheet, so if we know the function for this continuous AX, you just need to replace the delta by 2 delta to get the second movement of the actuarial present value random variable. And for the K, or the curtailed case, we can see uh, it's like this. So if you, not the curtailed case, before that, if we say in here, we said that the benefit is $1. So suppose the benefit is greater than $1. So you just need to multiply this actuarial present value of X of $1 by the actual benefit amount to get the corresponding actuarial present value of that benefit payment. So that says you can find this assuming the benefit is $1. After you find this, just multiply the actual benefit and it will give the actual present value of the actuarial the calculated present value of this K benefit, which is paid in future for a person who is at age X. And for the variance, it's again K times the variance of $1 benefit payment scheme. So now you see it's easy to work with, and it's just the notation we need to understand. So to understand the notation, let's quickly go through this example. So we are given that the force of mortality is constant and CB the present value random variable for the whole life insurance with a level benefit payment of $1 payable at the moment of death. It says now, so once you read these things, it says the whole life $1 benefit payment and paid at the moment of death. That means the actuarial present value should be capital A starting from X and continues. So derive the expressions for the actuarial present value and the variance of this uh, present or the insurance term in terms of mu and delta. So since this is continuous, we need to add bar to here. And let's start using from the scratch. So we know that mu x is equal to mu for all x's which is non-negative. And because of that, we can find the survival probability from x to t is e to the power negative mu t. Because if you integrate this and put into the negative exponent, so this is the value. And from the definition of this, we know it goes from 0 to infinity. And the present value is delta t for the interest part. And this is the fxt, which is pxt times mu. And we have it like this, and we can simplify it further like this. So now we have a familiar exponent function, and you can take mu out of that. And for this one, it's e to the power mu plus delta to the t and mu plus delta. Uh, the limits goes from 0 to infinity. And we know that if t is in infinity and becomes negative, that means the exponent goes to 0. And if the exponent is at 0, the exponent value is 1. So that I can simplify this like this. So mu over mu plus delta and 0 minus 1. And since we had minus in here, so if I take it out this, so the final answer will be mu plus delta. And so this is under UDD. So if I recall you in the final example in life table lecture note, so we had something like this. Under the constant force of mortality, this was this. And in here, the actual present value is mu over mu plus delta. So you can see a similarity in these equations. So this is the expectation of future lifetime. This is the expectation of the future benefit payment, which is discounted back to the present. Actual present value of the benefit payment of $1. So if the benefit was 100,000, we just need to multiply the 100,000 by this AX bar. And for the variance, So we need to first find the second movement of the actuarial present value of this scheme. And as I mentioned, you just need to replace delta by 2 delta. So this is the final value. And this gives us the variance of C as and okay, this is negative. So that is the variance for this continuously benefit paid whole life insurance who is at age X. And if these two values are given, find the probability that the net single premium is insufficient to cover the benefit. So in this question says the net single premium is, so if I buy this whole life insurance, I'm only uh, going to pay one time at the time of purchase. So I pay a sufficient amount at present, and that value will grow into uh, something which is equal to benefit at time of the benefit payment. But if I only or solely depend on the present value of the future benefit payment, so then as I mentioned in the description as well, there's a possibility of having insufficient balance to cover the benefit. So that means if I pay 50,000 and that 50,000 grows only for 90,000 by the time of benefit payment and the benefit payment is 100,000. So then the company has to bear the rest of the 10,000 gap for the benefit payment. So that means the fund is insufficient at the payment or when the payment occurs. But at some point, so this occurs during a certain period. So if I'm giving like for an example, if this person at age 25 by the time of purchase and from 25 to 30 the grown growth of this fund is less than 100,000, but after 35 years of age the growth of the fund will exceed the 100,000. That means if the benefit payment occurs between 25 and 35, the company has to bear the rest of the money. But after the 35, company has sufficient money from the single amount they got from this person when he was at age 25. So that means they can pay the benefit from the money they got from the insured, and they can keep the rest of the money to cover the operational expenses and keep it as the profit. So that is the picture. So that means to find such probability that the net single premium is insufficient to cover the benefit is our present value should be less than, so which means in here, the C is the random variable. So the actuarial present value should be less than the random variable, or in the other way, the random variable is greater than the actuarial present value of this payment. And the actuarial present value, which is equal to this, and we know the values of this, which is 0.001 divided by 0.003, this is 1 over 3, and Z is V over Tx, and this is 1 over 3. And Tx is a random variable, and here it is constant force of mortality. And I mentioned that when constant force of mortality occurs, Tx tends to follow the exponential distribution. So what I need to do is just transform this into an interval of tx. For that, I'm taking log value of both sides. So the natural log of v and is greater than the log of 1 over 3. And this is, so we can use this. 1 plus I is v, and 1 plus I negative log 1 plus I means log v. So this is a negative value, and it is equal to, we can find the value using this delta, because we know that this is delta. So this is equal to negative 0.02. So if you divide both sides by the negative 0.02, the tx is less than, now because we are dividing by a negative value, is 1 over. So this is the probability. And we can find this value using the calculator. And this is the random variable, which is an exponential random variable now. So for an exponential distribution with mean 0.01, this is the cumulative distribution, so definition of the cumulative distribution, and it is exponent mu is equal to 0.01 for the distribution, and these negative values come from the negative value corresponding to 0.02, and this is a number. So this is the corresponding probability, which is, if I use the calculator, should be something like this. So in here you can see, though we are dealing with the concept of the continuous whole life insurance in here, to calculate these probabilities, we need to stick to the probability distribution theory, uh, and also this simple transformation. So I used an additional knowledge in here with this, the definition of V and the definition of delta. So that's why I use this and then use the transformation to get T, and this particular probability says the cumulative probability of exponential distribution. So I can directly apply the form of the cumulative distribution function of the exponential distribution, which is given in the exam formula sheet. And you can use that function directly in here and substitute this value there along with mu and find the final value. So now you can see, if you get a net single premium for an whole life insurance, there's a chance of having a loss for the insurance company. That means once you get this actuarial present value of the whole life insurance, you need to add some profit loadings and expenses loadings to this actuarial present value to make it profitable, or at least make it break even. So for this case, you can see about 42 times. So if I sell this type of whole life insurance with net single premium, then out of 100 policyholders, I have to bear about 42 policyholders as losses. So that means for 42 policyholders, as the company, I have to pay some money for their benefit payments. But from 50, other 58%, I can generate a profit. So that's how I can balance uh, the competitiveness in the market and without having overpricing. So which means if you overprice a person, so that customer can move to a different insurer. So if you need to be alive in the competition in the market, and also you need to have sufficient amount of premiums to cover these expenses. So you don't need to get profits from each and every customer, but as actuaries, we balance these numbers and make profits from some part of the so which means we need to make sure that we will make profit of most of the customers, but there will be unexpected payments in future for some set of customers, which is which can generate a loss for the company, but that loss is covered from the generated profits from the other clients and the investment methods. So we are not going to overcharge the customers to cover those losses. So that's why we think of these different kind of probability distributions and these calculations to go then cover these expenses. So that is the story of continuous whole life insurance, where I will recall again, it is continuous because the company pays the death benefit at the moment of the death. And it is whole life because of the insurer will pay the benefit to the insured or the customer at any time of their lifespan. Uh, that is why it's whole life. And the level benefit means the benefit is level. That means if that person purchase the insurance at age 25, the benefit is same as at that time as at the end of the life after 50 years or 60 years. So that means uh, if we know the level benefit, actual present value, then you can multiply uh, different scales. But for an example, I'll quickly mention that one as well. You can see these level benefits in different ways. Suppose you have something in here. So from age 25 to 35, the benefit will be 100,000. And 35 to 55, it's 150,000. And for the rest of the life, it's 200,000. So this scheme is same as you are having a level benefit of 100,000 from 25 onwards, having another level benefit of 50,000 starting from age 35 and onwards, and starting another insurance at age 55 with level benefit of 50,000 from 55 onwards. So the same portfolio or the same insurance can be replicated using three different insurance products. So that's why we always think about the level benefit, because though you have different kind of benefits, still you can replace them with level level benefit products. So both scenarios are same. So if this person buys one insurance with this increasing pattern, so it's same as if that person is buying three different insurance at three different times with level benefits. So that's why we prefer to go with level benefits and define specific functions for level benefit cases for $1 benefits, and then you can multiply the actual dollar amount and get the actual present value amount. So that is the part one for today. Then we can have break and come back in. So this is like 2 hours from the lecture. We can have a break of for 15 minutes and come back. Then we can continue the rest of the lecture.